Hi, I am Milad. I'm here to present our work on traffic analysis. This was a joint work with my advisor and Arya, who is a professor in our department working on information theory area. Okay. The name title of our work is Compressive Traffic Analysis, and the goal is to come up with an idea to make the existing traffic analysis approaches more scalable. Okay. What do we mean by traffic analysis? For an example, assume you have a bad guy. He wants to send a message to a victim, but the bad guy knows that if he sends a message directly, can be detected much easily. So he will use a proxying system to hide his identity. Then the victim will tell the cop, and the first thing the cop do is to just see who is the sender of that message. Then he sees just a random guy in the internet running a proxy and tries to catch that guy. Then lots of uh, hype going in our community and saying that he's not the actual sender of that message and convince the guy that please go and find another one. So he asked a security researcher to find the actual sender of the message. And we, as a security researcher, we want to see find the actual sender of message by looking at the both sides of these connections. Another example of the traffic, and we know that this is a proxy. This is just a proxy, and we can find the actual sender by using some techniques of traffic analysis. Another type of traffic analysis is that, as Rebecca told earlier, uh, website fingerprinting is another type of traffic analysis, and you have an encrypted connection to a proxy in the internet, and you want to find out, you want to infer the website from the encrypted connection, and you don't have access to the destination of these connections. So the usual environment in traffic analysis is that all of the messages are encrypted, and in each of these proxies, the format of these messages are going to change. So you cannot use the basic methods such as DPI or just looking at the destination to find out the uh, uh, features you want. And therefore, you need to use the other features of traffic such as timings or size of the packets. In this presentation, we are going to focus on two types of traffic analysis, which are called traffic correlation as our first example, and that is the way that correlating traffic going through an anonymity network and to the packets are coming out of that network. And also, we are going to look at the website fingerprinting. What is the scalability issues in the what are the scalability issues in the traffic analysis? We know that most of the traffic, the number of the connections in the internet are growing fast, and also lengths of each connections are growing. So every day you are making more connections, and you are sending more data in each of these connections. And most of the traffic analysis techniques are orders of the number of the connections and the size of them. And we want to do the traffic analysis in the real time. But the existing methods, none of the existing methods look at the scalability of their method, and just they want to come up with the accurate methods. So the observation here is that we cannot change the number of the connections in the internet. But the other thing that we can do is that we can change the number instead of using the whole connection for the analysis. We can take some samples from that connection, and this method is called uh, dimension reduction. And we are going to use a specific way of dimension reduction, which is called compressed sensing. Compressed sensing is a technique in information theory, which has a lot of application in medical use and other types. But here we are going to apply the compressed sensing in the traffic analysis and make them more scalable. So what is the compressed sensing? As I told earlier, compressed sensing wants to reduce the dimension of the data. The one property the compressed sensing needs is that the data must be sparse for comparison sensing to work. And a good point about the comparison sensing is that comparison sensing doesn't require learning. There are several ways of dimension reduction in the different areas. For example, we can use PCA or a new approach such as autoencoders to reduce the dimension of the data. But all of these methods require learning on some data set to do the dimension reduction. And therefore, they are not generalized. And in networking and network packets, there are lots of different conditions, and it is hard to train your model on all of these conditions. So it is better to use a general method instead of picking some specific model. And how the comparison sensing works, assume you have a data with m dimension. You will multiply that data by a matrices which is called sensing matrices, comparison matrices, and you reduce your dimension of data to the n. And usually this n is much less than the actual dimensions. So, and if your data is sparse, you can apply some function to decompress your data and capture the actual data. Now guess what? The timings of packets in the network are sparse. We know that packets are usually bursty or have a constant bitrate. And we need our data to be sparse in some specific space. It could be a real timing space, or it could be frequency or something. So we can, since the data is sparse, we can apply the idea of the compressed sensing on the network flows and compress them, then we can recover them perfectly. But if we want to do recovery, this is just similar to using other type of compression method, even using a zip to just zip your files and then extract. Why we are insisting using compressed sensing? Compressed sensing methods usually have a property which is called a restricted isometry property, or RIP in short. And what is that? Assume you have an uncompressed space. For example, we have 2 dimensions, and you have a set of points in that space. For example, a set of red ones and a set of blue ones. When you compress them using that sensing matrix, you will reduce the dimension of data from, for example, 2 dimensions to 1 dimension. But as you can see in this figure, the red points which are near each other in the uncompressed space are also near each other in the compressed space. So the distance between each instances of data will be preserved. So we can now assume the red ones are, for example, website A in website fingerprinting, and one of the red ones is just one instance of the website, and another is another instance. Then when you want to find out the website of one of these points, you want to find which are the nearest point and which points are near to that website. So you can do that measurement also in the compressed dimensions. So you don't need to recover your data, and you can do your measurement on the compressed dimensions. So we are going to present our work, and we define a new paradigm for traffic analysis, which is called compressive traffic analysis. And the aim of our work is to reduce the complexity of existing methods. This is not a traffic analysis method. This idea can be applied in all of the existing traffic analysis. And the general idea is that you compress your data using compressed sensing, then do the computation. Okay. For first part of this talk, I'm going to focus on the traffic correlation, and then I'm going to show some example of website fingerprinting. For traffic correlation, there are several previous works, which most of them suggested that we can use the timings of packets to correlate the traffic flows in the network. And they also said that we can come up with other features, for example, packet counts or converting the flows to on-off streams, which are some variation of the timings. But for this work, we are going to only focus on the timings of the packets. So we have our security researcher here. We have a traffic flow, which is output of a proxying system. We have a proxy who adds some noises to any flow going through that. And we have a set of inputs. Now we want to find which of the flows from the input side is matched to the output target. So we do some kind of timing analysis, and we find that, for example, the red flow is not a good match, but if we choose a better blue one in slides, it's a good match. And we can find out the actual sender of the output target is the flow number 1, and we can find out the actual sender. So what is the complexity of traffic correlation? If we have S flows going through a proxying system, and each of these flows have at least m packets, the computation complexity is S squared times m. And we have also another type of complexity. We have storage complexity, since we have to store these data, and we have a communication complexity, since usually we have multiple sites and we have to communicate the flows between these sites. And these complexities are not scalable. To give an example, if you have just 10,000 flows and you want to do a full correlation between these 10,000 flows, it takes about a day to find a correlated flow for each of those 10,000 flows. What is our suggestion? The abstract model of the traffic correlation is that we have a guy who look at the two sides of the connection and want to correlate between these two sides. But the actual model is that we have a collector who collects the data in different parts of the internet, and we have a correlator who wants to correlate these collections with each other. So the collector will see a flow of packets. We will extract a set of features, for example, timings, and the correlator use the same exact features and find the matching ones if two flows are near each other. We suggest that after extracting the timings, you can compress them using the sensing matrix, and then for the correlator, you can do the same thing, and then we can find the correlation between the compressed version instead of using the uncompressed version. So we talked about the sensing matrix, and we said that that does have the RIP property. And how we choose that sensing matrix is that we have two types. We can have a random matrices, and which is each element of the sensing matrix is sampled from a random distribution, or we can have a deterministic matrices, which there are some formulas in the information theory area which can generate a matrix. The random Gaussian gives us the best theoretical results, but we can use a random +1 and -1s. And the intuition for the +1 and -1 is that if we use +1 and -1, we don't need to do the floating point multiplication. +1 and -1 is just adding and subtracting some of the timings from each other. And that can be a little bit faster than random Gaussian. And how we are going to correlate between two flows in the network? There are two general ways of correlation. You can have an optimal correlation formula or some general formula. For optimal, you usually assume your network timings are from a specific probability distribution, and you use those assumption about the network flows and the noises to find the likelihood of two flows being correlated or not. The problem with using optimal correlation is that computing those probability distributions are usually expensive. And also, they are optimal for a given set of parameters. For example, if you set that the network noise has a specific mean, it should have that mean. And it is optimal for that mean. If the network noise is a little bit different, this is not optimal anymore. Or you can use some more general correlation methods. We have both of the results in the paper, but for this presentation, I'm going to just continue with the more general correlation. And we used cosine similarity for finding correlation between two flows in the internet. A good point for using cosine similarity is that we can design a good data structure to be able to do the searching much faster. A usual way of finding a correlated packet in the internet is that you have a data set, you are enumerating in all of the records of that data set, and you find out that one of these records are highly correlated to your target flow. But this usually takes lots of time. The other thing that we suggest that we can do is that you can, since you are using a specific, for example, cosine similarity, you can do some kind of indexing in a way that if all of the points have same index are near each other in cosine similarity space. So when you want to find the correlated packet for a flow, correlated flow for a target, you just go to that index and just search areas in the instances in that index. That can help us a lot in saving time. We evaluated our method using some data traces, and also we captured a lot of network flows from the different analytic networks. We measured the network noise, which is called jitter noise, using Planet Lab nodes, and we find out that we can estimate the network noise using the Laplace distribution for the optimal correlation. And for the result, here we see that if we use compressive sensing, compressive traffic analysis, and compare it to just simple sampling method, we can get about 10% more true positive, which is a lot. And also, the false positive rate is much less than a simple sampling method. And so we are not losing anything by using compressive sensing in these scenarios. The main intuition of this work was to make the existing method much faster. So here, if you don't use any type of speed up for a single query, for finding a single correlation, for finding a single correlated flow for a target, it takes about 5 seconds for a data set of 7,000 flows. But our approach takes about 4 milliseconds. And if you want to do a full correlation, it takes about 10 hours for this non-compressive methods and only 5 minutes with our method, which is a lot of speed up. We are not the first one who are trying to do these kind of dimension reduction and sampling. As you can see the results in the right, we compared our work with just one existing method, and we saw that our method is more accurate than the previous work. And also, we compared our optimal correlator to an existing optimal correlation method, and we get the same results. Okay. This was the first part of my talk, and the second part is about website fingerprinting. As I said website fingerprinting is one way of doing traffic analysis. And website fingerprinting also use the timings and sizes of the packets in the internet. And there have been lots of previous works in website fingerprinting. For this presentation, I'm focusing on only two of these works, and there are two main general way of doing website fingerprinting. One of them is using KNN and in-memory type of machine learning approaches, and one of them is SVM, which have a model and train on data. And both of those works has been accepted in the top security conferences. So the general way of traffic analysis, the website fingerprinting, is that you have three main phases. You have feature extraction, you have training, and you have prediction. You extract some features from your website traces, then you do your training on those extracted features, and you train a model, and then you use that model to come up with some prediction for new instances that you get. We're suggesting that we can compress the features after being extracted and do the training on that compressed feature set. And by doing so, we can make the existing method more scalable. And to give some results, we applied our method in two existing works. For example, the work by Wang, the KNN method, have about 3,000 features. And if we don't do any kind of comparison, website thing, the runtime of their approach takes about 33 minutes. But if we do comparison, we can get about 13 times more speed up and just losing 5% of accuracy. And we also applied that same approach to the SVM work, and we get 3 times more speed up with only 3% less accuracy. So the result of this work is that we changed all of the dimension of our data from M, which is usually a large number, to an N, which is a smaller number. And we showed that if you use a better search algorithm, you can reduce your computation complexity much. You can reduce your computation complexity. And our improvement is that if you want the same accuracy, using compressive sensing method can do it in a shorter amount of time. And it is more accurate than any existing sampling method for the traffic analysis area. And to conclude, we showed that the existing traffic analysis methods are not scalable. We need to use some generalized dimension reduction technique, and we showed that we can use compressive sensing, and compressive sensing have lots of benefit for us. And if we can find a better search algorithms for different areas, we can get a lot of speed ups. Thank you very much.
Okay, if there are questions, please come up to the mic.
I saw your website fingerprinting work. Accuracy loss is not that significant, so we achieve very good result. But my question is, accuracy loss means how about in terms of true positive rate and false positive rate?
We showed the same, and we used the same metric as they present in their paper. So
Okay.
they used the actual accuracy, and we showed the accuracy. But this true positive, and we use it for the open world scenario as well. And the true positive and false positive is the same as the.
Okay. Second question I have. So you were talking about scalability. I was thinking you can apply, say, big data technology like Spark, where you can do the distributed computing. That may provide some scalability issue. I mean, that may address scalability issue also.
You don't reduce the complexity of your
Right,
data.
but you can, our main objective is speed, so
Yeah.
that's another way you can achieve the
Yeah,
speed.
you can do this distributed
Right.
computing.
But it may cost you. Okay, thank you.
Hi, thank you for your speech. I haven't read your paper yet. So by using your method, I believe there's some information loss, right? Like there are some property between within the flow or between the flow. So if we use your method, is there any property that cannot hold?
It usually depends on your measurement technique. The RIP property is keeping the Euclidean distance metrics. So lots of these properties are some derivation of the Euclidean distance, and all of these will be preserved. But it depends on the actual property you want. You must investigate if the compressed sensing preserve your property or not. But if your property is derived from the Euclidean distance, it will be preserved.
Okay, so is that tunable?
Yes, it's tunable.
Okay, cool. Thank you.
In one of your slides, you show there's one of the curve show compressive sensing plus LSH, locality sensitive hashing, right? Just want to know, have you tried just use LSH? What kind of performance do you get without compressive sensing?
I
That will be-
didn't have the results, but you usually have the speed up just in the searching complexity, not through
But LSH itself is a
Yeah.
dimension reduction, so right?
It could be.
Because it's a compare similarity.
Yeah.
Know that. So
Uh,
that one may, how much gain do you have if just apply LSH?
I don't have the result for the just using the LSH. And
Thank you.
Okay, I'll just ask one quick question. Can you just talk a little bit more about your open world results for website fingerprinting? Because if you're talking about a 5% loss of accuracy, that could be pretty substantial.
Unfortunately, I don't have the results for the website for the open world scenarios. But as far as I remember, the loss of accuracy for the true, usually we don't change the false positive, right? We usually reduce the true positive. So it's not going to impact a lot because the false positive is very important. It's much more important than the true.